Hey, this is Steven from the Green Engineers, and welcome back to my research video series. We are back looking at some 3D printer material properties and comparing them to each other. Again, I'm going to put my, my required knowledge prereq for this video, which is go onto my channel and go into my research video series. One of the first few videos I released in the research video series was how to read mechanical property data sheets, or the technical data sheets, the TDSs. So in that video I go over how to read mechanical properties and what each mechanical property is. You're going to need to know what those mechanical properties are to understand what I'm talking about in this video. So go into my research video tutorial series, and then towards the beginning you'll find a video that has all the the required knowledge to understand this video in there, and I will try to put that inside of the description box as well. So if you have not seen it, you can go see it, and when you finish watching that, go ahead and come back, and from there you'll be able to go on to any sort of website that has materials and be able to read them and compare them apples to apples. And also be able to understand this video. So go ahead and go watch that and come back, and if you've already watched that, welcome back, and let's go ahead and start the video. So on today's video I wanted to look a little bit into some reinforced composite materials for 3D filament printing. So one of the nice websites, I haven't used these guys yet, so I'm curious to use these guys, but I like how they are running their service here. As far as on the home page in the toolbar, they have a technical data piece that brings up every single technical data document for every single one of their 3D printer materials, with all the mechanical information that you need in there. The temperature, the TG temperature, the yield, you know, the strain, ultimate strain, the tensile strength, the flexural strength, the modulus, everything. Everything is in there for every single one of their filaments. And 3DXTech seems to be a very big manufacturer of pretty much any sort of filament that you would ever want to get. Except for what I see missing here is they do not have any sort of flexibles. So as far as what I've seen here, if you're looking for flexibles, 3DXTech does not have it. Alright, yeah, so let's see what we got. We got electrostatic discharge safe filament, PEI filament, polycarbonate ABS mix, polycarbonate ASA mix, and just standard polycarbonate, PETG, nylon. And by the way, their nylon is like a nylon reinforced, so like it doesn't, I believe it doesn't flex very far. Standard ASA, ABS, high temp PLA, which this is a NatureWorks high temp PLA, Ecomax PLA, which it doesn't say it's NatureWorks, so I'm curious if it is NatureWorks or not. HIPS, high impact polystyrene support filament, which is basically dissolvable supports. Extra large reels, which are very, very good discount for extra large reels. They sell them in 4 kilogram spools for a very, very good price per kilogram. Plastic pellets and colorants for like a machine like my multi-extruder, or other machines like the any sort of filament maker, like the multi-extruder or the fill-extruder or the filamaker or anything like that. So they have plastic pellets of pretty much every single one of their materials in there to make your own filament if you wanted to, and also pretty much any colorant that you would want. They also have A2 hardened steel nozzles, very, very nice. So if you're getting into printing a lot of abrasives, like any sort of thing that has any sort of hard reinforcement, like carbon fiber or anything like that, you can get your nozzles from here. Pretty good. I saw like one of them was like 29 bucks for a 0.4 millimeter. Also, like one of the best choices of sizes that I've ever seen on nozzles, on hardened nozzles. So almost any sort of millimeter that you want will be in there. Kapton tape, blue painter's tape, mylar pouches for your pellets or whatever, samples, and sale and clearance. So on this video, I would like to check out most of these in the video series, but in this video we're going to be looking at the technical specs for the carbon fiber reinforced. Very curious about the carbon fiber reinforced filaments and how they compare to standard PLA and standard ABS. So what I did, went on to here in the technical data, and I grabbed the PLA, Ecomax PLA. I grabbed the, also one of the things that they don't have on here is they don't have the high temp PLA, the Ecomax high temp PLA. But yeah, that's basically NatureWorks. You can go on their website and look up the high temp PLA on NatureWorks resin and it'll tell you. Hips, so I grabbed the PLA and I grabbed their, this one, the ABS, and then I grabbed all of their Carbon X. All their Carbon X are carbon fiber reinforced filaments, right? So I grabbed all those, and so now I have the Ecomax PLA, the ABS filament, which is the 3DXTech ABS 3D filament, Carbon X, carbon fiber nylon, carbon fiber PETG, carbon fiber carbon fiber ABS, and then carbon fiber PLA. So let's go ahead and organize these in probably what you're more familiar with. So they have four carbon fiber. They have 4 different carbon fiber resins that they use. Again, PLA, ABS, nylon, and PETG. And those, of course, are mixed with the carbon fiber strands that are cut up and put in there. They also have those pellets available if you go to their pellets, and you could buy those and be able to make your own filament. Another thing that I wanted to say quickly about the 3DXTech that I really like is if you go in here, you look at their Carbon X, where is it? So this one is 0.0 plus or minus 0.05 millimeter, which is very good. Some of their standard PLA is plus or minus, I think their Ecomax PLA is plus or minus 3/10ths of a millimeter, so 0.03 plus or minus. So that is extremely good. Most companies will not even claim to do that. Oh, so I guess they don't have that. Do they? Yeah, so I guess they don't have. Okay, so we are missing one. They don't have the technical data sheet for this one. Oh, this is the really high extruder temp, so you need an all metal. So we won't go over this. Most ones won't be able to do this, but we could take a look at it after, because it has a few things like the TG, the temperature to glass transition temperature. All right, so let's go ahead and get started. So first things first, Ecomax PLA, which oh, here we go. It says using premium NatureWorks. So it's NatureWorks, and this is the non-high temp. So this is probably the 4043D, not the new one, the 3D850 or whatever it is, which is the one that you could anneal. All right. So here we have some. We have all standard metric units here on this one. This one's metric. Okay, so we're good here. Let me see if I could maybe be able to like. So what I'll do is I'll have the PLA and the ABS side by side, and then we'll go through them on this side and compare them. So that way we could see split screen here. Also, another thing, if you guys hear a lot of noise, it's like crazy storm going through California right now, like 25 mile an hour winds, 25 mile an hour gusts, so crazy amount of wind going on up here, or even more. So yeah, so sorry if you hear a lot of gusts and rain like hitting the window, because it's coming in sideways. That's how windy it is. So yeah, crazy storm coming in, so sorry about the interruptions if you hear anything bouncing off the window. Alright, so here we go, Ecomax PLA. We're testing a few things. We're looking at the TG, the glass transition temperature, the heat distortion temperature, the electrical properties, we don't need that. Look at the density also, take a look at the density a little bit. Tensile strength, tensile modulus, tensile elongation or break. I'm going to kind of skip over this. These are usually the same as this, but with plastics it's a little higher, right? Flexural strength is 115, so it's like double, so it's a little bit higher. But that's just going to take extra time because we could just compare from here to here, and then we'll look at this. So you see that flexural strength is almost identical here. Okay, so Carbon X carbon fiber reinforced PLA filament. So how much stronger is the carbon fiber adding to the PLA filament? So here, I don't know if it tells you. So here's NatureWorks with the carbon fiber in it. Oh, layer height. There's spray on glass. So everything here, extrusion temp's the same, all that stuff's the same. So these tests are standardized, so apple to apples here. Alright, so let's take a look. So here, tensile strength, very weird. PLA is higher. Standard PLA is higher than carbon fiber. So here we're also kind of seeing if that myth stands up, that if carbon fiber actually helps the material, is actually reinforcing the material. So carbon fiber, 47.9 megapascals, and you notice that is ISO 527 standard, ISO 527, so exact same. So everything in here is the exact same standard. So we could compare apples to apples here, and exact same properties here. So 47.9 to 56. So PLA is already higher ultimate strength before breaking. So what pressure does it take before breaking? PLA is higher. Tensile modulus. Whoa, but there you go. There is what we're talking about there. Wow. Tensile modulus in the carbon fiber reinforced is almost, not quite double obviously, but it's almost double. It's almost double the stiffness. So if you remember from that video, that is the vertical, and the stress strain. So here's stress, here's strain graph. That first linear line there, what we call the elastic region, this tensile modulus is the slope of that line. So it's in basically stress, how much for a certain amount of stress, what's your strain. So how much, and again, strain is the stretch, right? Is how much it deforms. So that means that the carbon fiber reinforced takes twice as much force to get it to deform the same amount of distance. So sure, the ultimate stress is lower, but the slope of the line is quite more drastic. Because most of the time you're not going to, in most parts, you're going to, be below this and below this, but even if you're below this by like 30, you're at like 30 megapascals load, you're gonna make way better, stiffer components out of 4791 than 2865. So any sort of application where you want the part to be stiffer, so not deform as much, you're gonna want the carbon fiber to be inlaid inside. But we have a downfall there. Because of the stiffness, we have a drastic loss. Generally, a material that has more stiffness is not as ductile, is more brittle, so that means that it tends to snap without bending too much. And we see that there with a 2% elongation before break, and then a very interesting 8% for PLA. Because normally when you go on the NatureWorks docs, it says that it has elongation of like 3 to 4%. But we'll go off of these guys. So 4 times more elongation before breaking. So this is a way tougher material than the carbon fiber reinforced. Again, flexural modulus, you'll actually see here in the flexural modulus that it is actually drastically better in flex. So if you have a part that you're using carbon fiber, when you design it, have it in bending instead of in pulling, right? Have it in a flex instead of pulling, and you drastically increase your modulus there. So this one's just a little bit, it's just as good as tensile as it is in flex. So overall balanced material. This one drastically more flex strength, drastically more flex stiffness than the tensile stiffness. And then finally, flexural strength 114, and you see that the flexural strength is now on par in bending with the PLA. So we'll actually almost beat out PLA in flexing, you know, compared to its tensile strength, which was quite a bit lower. So very, very good in flexing, extremely stiff material, but extremely brittle material. So this is very interesting. And then we see the glass transition temperature didn't change much, 60-60. Temperature, heat distortion temperature at 0.45 megapascals pressure is 56.2, 54.7. And the density changes 0.05 grams per cubic centimeter. So very interesting, a little bit more dense. Supposedly with this one, it keeps its dimensional stability when compared to unfilled. So a little bit better dimensional stability when compared to when you heat it compared to PLA. A little bit better. And then also people say that this one doesn't technically distort as much as when printing as the PLA. Alright, so let's see how much the carbon fiber PLA blows the ABS out of the water. So now we're on the ABS. Again, oh, ABS got very low density. That's interesting. Tensile strength 41, pretty close. So actually their tensile strength for ABS and PLA is pretty close, but you know, 15 megapascals for plastic is quite a bit, right? So PLA is quite a bit stronger material. Tensile modulus very low, even compared to their PLA. It's not quite half, but maybe 2/3 great. It's maybe like 2/3 greater or 2/3 less than PLA. Here we are looking at way over double. So way over double stiffness in tensile, but here we see that it has 5 times the stretch before breaking. Flexural modulus is more than 3 times better in flex, and we see that it's actually just tiny bit better in flex, and yeah, but quite a bit higher ultimate stress before breaking in flex. Very interesting there. But obviously you see here, bed temperature, you could print with 23 Celsius, so 24 Celsius is like 76 degrees Fahrenheit. And so you can see that you could have it just room temperature or 60 C, but here you want 100 to 110 C for ABS. It's quite a bit better stiffness for, you know, a lot less the heated build plate. But look at the dimensional stability, glass transition temperature, 105 degrees Celsius. So almost double that of PLA. So if you put this on the dash of your car, it's not nearly going to deform it as much as the PLA, even with the carbon fiber filled. Here, heat distortion, again, 100. Here, 56. So again, almost double. So ABS, more ductile, definitely not as stiff, definitely not as strong, definitely not as stiff in flex, and definitely not as strong in flex. So, summing it up for carbon fiber reinforced PLA, great for use in machines that take load and need to maintain its dimensions while on load, not to distort, in flex preferably. But even in tensile, which is pulling, that would also work good as well. So when you're designing a machine, you're going to want to use that when you have possible flexing issues. And yeah, looks great. Alright. Obviously in this, you also don't want it to flex too far. So limited flex, very limited flex part. You want to minimize flex. Yeah, because otherwise it's just going to break, because it only does 2% of its original length before breaking. Alright, so now we're on to the next one, which is the carbon fiber reinforced ABS. So now let's compare the PLA to the ABS here. So what we'll do is now we'll move this guy. Whoa. Now I'll move this guy here and also have that compared to the ABS. Alright, so we're going to go quicker through these now. We're already at 20 minutes here. So tensile stress, PLA, standard PLA, 56 compared to 44. We'll look at the ABS here in a second. Wow, double the stiffness. We'll compare that to the carbon fiber, but that is really high. But you see the loss. You get so you see the loss in flex here. So the loss in ultimate strain. We went from 10 to 2 to less than 2, right? So drastic loss there. We doubled our modulus, increased our tensile, and then a little bit under, still not nearly as good. It's about the same as ABS, which we saw PLA versus the carbon fiber PLA. Because the matrix is the part that fails, so when you have a reinforced, you have the matrix and then you have the reinforcement. The matrix is basically the resin, and the reinforcement is the carbon fiber. So your ultimate stress has to do with your matrix. So your ultimate stress doesn't really increase from reinforcing. What does increase is the stiffness of that material. So you want that material to be very flexible and the material put inside to be very stiff. So that way when you flex your material, the ultimate failure point is as good as the original material. But as you see here, it drops it drastically, because when you put a stiffer material in there, you can't necessarily maintain the same properties. So it drastically, got rid of all your flex with the ABS. So almost double that here, dropped it by a fourth. Flexural modulus is a little bit better, not nearly as good as the PLA and flex, the PLA carbon fiber. Flexural strength, still not. This is really good. This is really good. This is double that. So this is definitely not double that. But where you're going to benefit is the stability, the temperature stability of the ABS, which is 105 versus 60, and then 55 versus 102. So this is almost twice as stable, twice as dimensionally stable in temperature. All right, standard ABS, tensile stress, again, as we've seen, not too different. We see that you increase the density by 0.06 grams per cubic centimeter, so a little bit more dense, a little bit more heavy. You double the tensile modulus. You drop the tensile elongation by a fifth, 1/5. Flexural modulus, almost times 3, maybe like what, 2.5? Yeah, a little bit over 2.5. So a little bit over 2.5 times the tensile modulus there. Here, 2.5 times. Flexural strength, identical. So you're limited by the matrix of the piece. Doesn't really change the glass transition temperature. A little bit here. Right, so a little bit here. So a little bit increased stability. So for the carbon, compared to the carbon fiber PLA, still quite a bit. What was this one again? Yeah, so here you lost the tensile stress here, but you increase in ABS, right? Yeah, so you increase a little bit. So here you increase a little bit in ABS. 4791. So just a little bit higher there, but drastically higher here. And quite a bit higher here. So, but you see that, of course, the stability is the same. So again, with the ABS, do you have to change the bed temperature? No, it's the same print stuff, same print specs. So Now, carbon fiber PLA versus carbon fiber ABS. So where the carbon fiber ABS would be used would be if you have something that is under a thermal load and you want it to maintain its shape under temperature. Not necessarily load, it's still good at load, so it could do both. So when you have something that is loaded with weight, so some sort of machine part, and it's under temperature, right? So here that's 105C, so that is, well, let's say 102C. So that's almost 200. That's almost 200 degrees Fahrenheit, right? So up to 200 degrees Fahrenheit, you're going to maintain pretty good stability, right? So you have a machine part that could hold quite a big load, as well as be under heat and not really deal with anything. But you lose all the elongation of ABS, but you gain a lot of strength and stiffness. So also you notice that this is quite a bit less dense. This is almost 0.2 lower, 0.2 grams per cubic centimeter lower than the PLA. So it's lighter and it has better temperature stability. But it's harder to print because, as you know, ABS flexes like crazy. So I don't know if I would use this still even without a heated chamber unless you're building really small parts. The smaller the part, the better the ABS is going to print. So what would I use it for? I would use it for anything, like I said, a machine part or a high stress part that needs to maintain its shape in high heat. But also again, not flex so much, and also it's light. You want the design not to flex nearly at all. So minimize flexibility, because if you go too far, you're going to break it. And it's slightly lighter, but harder to print, right? Way harder to print than PLA. So you need a specific type of machine to print that. Alright, on to the next one. Carbon fiber nylon. So we're looking at PLA, standard PLA, a little bit higher by 6, 7, 8, well it's basically 8. Wow, double the stiffness there. And this one is double the elongation of most of the carbon fiber, because this again is the carbon fiber nylon. Nylon's known for its flexing. So 2 times the flex of PLA ABS. Flexural modulus 5650, flexural strength 78, 105, 102. So now that we see that and we've compared these and we know how these compare to these two, we'll just look at the difference between the carbon fibers now, right? Because now that we have both the PLA and ABS in, these are basically the stiffer versions, so we can compare them apples to apples. Because now you have carbon fiber PLA, carbon fiber ABS versus a nylon PETG. Because these are pretty uncommon. Usually you have PLA, carbon fiber filled PLA, and then sometimes carbon fiber ABS, but you never really find carbon fiber filled nylon or PETG. Okay, so 47, whoa, nylon, very high tensile strength, also lighter by quite a bit, so about the same thing as the ABS, so quite a bit lighter, higher tensile strength, which is shocking to me. 4,400 for the tensile modulus, 2 times, 5650 for this, a little bit under, and then here is 78, which is quite a bit under this, like 40. Glass transition temperature 105, 102. This one also needs a heated bed. 240 to 270, so all metal hot end here, otherwise you're going to start melting any inserts you have in there. 100 to 110. Alright, so this is an interesting one because it seems to almost beat out the PLA as far as a selection that I would personally pick. But let's take a look at the ABS compared to it first before we make that consideration. So 63.9 to 44. Whoa. 41.8 to 5260, a little bit more dense by 0.03 grams per cubic centimeter. Better, 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 just as good. Same, a little bit higher temp, a little bit higher temp. So, obviously, if you had the choice, you would pick the carbon fiber nylon over the carbon fiber ABS, because there's anywhere in the ABS that it beats the nylon, except for that you're going to need an all metal hot end to print that because of its higher temp. And also, you know, anything that would be in the carbon fiber nylon would probably be the water retention, and then maybe how difficult it is to print. It might be more difficult to print, but other than that, it beats the ABS. So no reason why you'd pick the nylon over ABS. So if you had a choice between nylon and ABS, pick the nylon. Beats out everything in the ABS. And then who knows? Maybe it's even easier to print. And then if it's easier to print and it doesn't you know, curl as much, then like no point in picking the ABS. Nylon beats the ABS hands down. Here though, you have a drop stiffness, double the elongation, double the flexural modulus. I mean a little bit. Sorry, this is a little bit under, and this is quite a bit under. So now we have the difference between nylon and PLA. So obviously now the fight is between PLA and nylon. ABS is out of the fight. Nylon beats it. So stronger in tensile strength, you know, a little bit tougher, probably a little bit tougher material. Yeah, definitely tougher because it has 2% elongation more. So it would probably be neck and neck with carbon fiber PLA as far as your machine choices that you would use it for. Nylon would be something that you want to be tougher, stretch further before breaking, have just almost better tensile strength, pretty close stiffness, so pretty good load to deformation relationship. Flexural modulus is pretty close also, but flex is definitely not as good. So if you're in tension, you're going to be just as good as PLA, and also stretch twice as far. But where it makes up between between that and PLA, number one obviously is it's less dense, so it's lighter, and also the temperature stability, the dimension stability under temperature, which is almost double. So for the nylon, if you have a machine that you want to have big stresses that would work stresses that would work also for PLA, and you want it to maintain, and it's under heat load, I would probably pick the nylon over the PLA. Except for in flex. In flex you would probably want to pick the PLA, but if it was just like a link that was holding something up, you know, then you would probably just pick the nylon because it even stretches further. So yeah, for me probably if I was using any sort of heat load, I would use this one. If I wasn't using a heat load, I would use this one. That's basically what it comes down to. So no heat, that's your pick. Alright, last one. And then of course, like we said, there was this one, which is like ridiculous as far as you need to print 330 to 350. So that's pretty crazy. Most printers can't do that. And also they don't have a data sheet. Maybe I'll ask them, see if they have a data sheet, and see what's going on. Okay, so back to the carbon fiber PLA, carbon fiber ABS, and then carbon fiber nylon. I don't know if I'm even going to do carbon fiber ABS because the nylon beats the ABS. So if this beats the nylon, then you know it beats the ABS. Alright, carbon fiber PLA. Alright, let's take a look. Whoa, stronger, bigger modulus, more flex, not as good in a flexural state, so not as good in bending, and not as good as in bending. A little bit better stability, but you need a heated bed, right? Not nearly as hot, so maybe you could get a printbot simple to hit that temperature, possibly. Okay, so carbon fiber PLA versus the carbon fiber PETG. I'm reading the little paragraph above. Yeah, so anyways. Yeah, so almost beats out PLA. You get a little bit more flex, better temperature stability, better tensile strength, a little bit more dense the PETG than PLA, not much. Almost as much flex, but it seems like PLA is incredible under flex. And that compared to, of course, like we said here, not nearly as high here, so higher here. This is standard PLA, yeah. So just comparing. Yeah, so it's better temperature stability, needs a heated bed. Okay, so versus PLA, probably would pick, this is probably one of your better bets, all around bets versus PLA. It's one of the better ones to pick. However, you need a printed bed. Here it's saying the test was at 65C, but this one was also 60C. So these are almost, one and the same here. And so yes and no. It could have some better properties in some states, and might beat out PLA. So here, kind of neck and neck, but also again better stability. But you need a different type of setup on printer, and what you need for definitely higher prints. So this probably won't work as well in your printer as this one. So you'd probably pick the PLA. Alright, carbon fiber nylon, drastically better tensile strength, almost as good tensile modulus, almost twice as much elongation, almost the same amount of flex, modulus, almost the same amount of strength, higher temperature. So, nylon, and also quite a bit less dense, 0.20 grams per cubic centimeter less. Alright, so the carbon fiber nylon versus the carbon fiber PETG, I would probably still pick the carbon fiber nylon. It's got better tensile strength, almost as good stiffness, twice the elongation, almost the same bend, and a little bit lower flexural strength, but more temperature stability and more heat distortion under load stability. But slightly different as far as this printing range. Almost the same extruder, so if you could print the PETG, you could print the carbon fiber, but you need to hit the bed temp. Here he's hitting 110, and here he's hitting 65. So obviously almost twice as much. So if your printer could print bed temperatures of 110, I would do the nylon. And also that should be the same for ABS, right? Yeah. So I would hit the nylon rather than the PETG. So if you can only hit 60C and you can hit those the extruder temperatures, then I would do PETG. So between these two, it would be what your printer can print. If your printer can't hit those bed temperatures, the heated bed temperatures, I'd go PETG. If it can, I would do the nylon. And that's how it comes down to it. So PETG, so it looks like here in the combination on my picks, the best ones are probably PLA. PLA for ultimate stiffness if you have no heat load. So ultimate strength if you have no heat load, but your design you're trying to minimize flex. Nylon is going to be your all around, good strength, not as good as PLA, good heat ideal temperature resistance, and maintain its stability. Also very tough, will flex a long way, so if something happens and your machine gets beat on or whatever, it'll stretch twice as far before breaking. so that you could later see the bend in that part, replace that part without it failing. Yeah, ABS. Well, here ABS, like, I mean, if you could print the higher temperature, go with nylon. Nylon beats ABS hands down, easy. ABS just kind of loses what it's good for, which is its flex, and its tensile, and its, you know, its temperature stability is pretty good. So, but if I were to pick between ABS and the nylon's got way better properties. So, for ABS, I don't know. I would pick ABS if I couldn't hit 260C. If I couldn't hit 260C, I would use the ABS. But other than that, I would use the nylon. So, use the ABS if you can't print the nylon. And then if you're going between PETG and the nylon, if you can't print the nylon and you can print in, like, you have a lower bed temp, I would pick PETG over the ABS, right? Unless you really need these high temperatures, right? So if you can't print the nylon, the next best is the PETG. So I guess if you can't print the nylon, then you're not going to be able to print the ABS. Then you're going to pick between the game is between the PLA and the PETG. And those have, you know, pretty good. So if you can't print this, you can't print that. So you're probably limited to this and this, right? And I'd probably say print this if you're under heat load. And then if not, print this. So these are pretty good. This is like the ABS versus the PLA kind of thing. And then this is like way better than ABS. So again, PLA ultimate strength, no heat load. Nylon. Nylon is heat load, high strength, almost as high as PLA, and also high flex. So basically all good properties right there, very balanced, but requires a lot of different specs to print. So if you can't print that, then the only thing I would do, and I need a very high temperature, then I would do ABS. And then basically the PETG is in between the carbon fiber PLA and the carbon fiber nylon. So I'd pick the PETG if I couldn't print nylon or ABS, pretty much. But other than that, you know, I would go with the nylon. Alright, so that's basically it for this video. This has been Steven from the Green Engineers, and I would like to thank you for watching this video in my research video series. Please subscribe for more videos in this series, and I'll see you guys in the next video. Thanks for watching. Take it easy.